Hey everyone, this is lecture 2 of week 1, and we're going to finish the review of the preliminary material. This lecture, we're going to talk about mean, variance, correlation, and squared correlation. And these are all very important concepts. We'll go through some of the formulas, but also some of the underlying concepts because we're going to be using them all semester long. So, and in the lab exercises, you'll have a chance to work through some mathematical examples of these. Even if you feel like you know this stuff cold, please go through all the material because there may be a few details that you didn't know. Also, there's a little puzzle for you to solve partway through the lecture. So pay attention, get your pen ready, and here we go. We are going to talk about descriptive statistics. That is the name that we give to some of the simple things like mean and variance and the statistics that just describe the data set. So first of all, mean, and the typical notation that we use is there'll be a variable name. And I'll zoom in a bit here for you. Don't want you to miss a thing. Variable name is y, and then if we put a bar over top, that's usually going to denote the mean of that variable. While I think of it, if instead we put a hat on top like that, then that means it's the estimate of y. So a bar is going to denote the mean, a hat will typically denote the estimate. So y bar equals, well, we've already seen this, the sum of the individual observations added up over the sample, which we'll say in this case runs from 1 to n. And again, I can zoom in a bit closer because the subscripts get a bit tiny, and divide by n, which is our sample size. With the summation notation, so if I write sum I equals 1 to n yi, I don't always need to write those bounds on it. So sometimes if I just write that, that'll mean the sum over the entire data set. And you don't need the I equals 1 to n if it's clear in the context. And n is the typical letter I'll use for the sample size. And this capital sigma, that's the summation operator. And if you've done calculus, you would have encountered the integral sign, which looks like that. And it kind of looks like the same thing because you've got an integral from I equals 1 to n. You get the bounds on the integral. Well, this is a Greek S, and this is a, well, it's a curly S. I don't know if it's in a particular alphabet. And that's not a coincidence because an integral is a summation. It's just a summation over infinitely small sample units. But we won't be doing any integrals with one exception. Yeah. So you don't have to know integrals for this course. So notation y refers to the mean of y. And a further bit of notation is if I just write the variable name, then I'm referring to that that whole category of observations. If I put the subscript either I or t in the case of time series variables, then I'm referring to a single observation. So this might be what would be the stock price. Let's say there's a corporation, Apple Corporation or something, and so I might say Y is the stock price of Apple and YI is the stock price of Apple on a particular day. The mean, what are we calculating when we calculate the mean? Well, it's kind of a central point. So it's associated with the center of a distribution. And a lot of data that we look at, when we say it's distributed, it means some have a low value and some are close to the middle and some have a high value. And in between, a lot of data, so if this is Y bar, a lot of the observations tend to have a bell-shaped distribution. So many data series have a bell-shaped distribution. It's not a law of nature or anything. There are lots of exceptions, but what it means is we expect most of the observations to be in the neighborhood of the mean, and then some will be farther away. So with the height example, you wandered around campus with a measuring tape and you measured lots of people's height. Well, most people are average height, and then there are some who are very tall and some who are very short. Now, I'm looking at the image here on my screen. It seems to be a little out of focus, so I'm just going to hit the autofocus button there, and it'll feel like you're at the eye doctor's for a moment, but I think that's a little better. All right. So we have the mean that tells us the center point here, but of course we need some way of summarizing the spread as well, because you might have some data sets where everything is really closely clustered around the center and almost nothing is out on the wings, and you could have data that's quite a bit more spread out. So what we need is measures of the spread. So one of them will just be the range, which is the difference between the minimum and the maximum. So in our earlier example, the range in this case goes from about here up to here, and in this one it's from here up to here. So the range is informative, but it's easily manipulated by an outlier. Was that on? Yeah, there. It's easily manipulated by an outlier. So if you think of the range of marks in a course, it may be that in a particular course the marks are all clustered around the average, but there's one person that just had a really bad day and they got 5% on the exam. So you can have a wide range even when the data set's clustered. So we need a better measure typically than just the range, and so we will use the standard deviation and the variance. So we'll start with standard deviation, and the formula is S equals, now here we go, 1 over n minus 1, so that's 1 over the sample size minus 1, multiplied by, and then we're going to take these deviations around the average squared, and then we take the square root of all of that. Okay, now here's the puzzle I want you to solve. All right, on the textbook, in the textbook, on page 13, spot the error. All right, so and I can complete the notation here if you want. I equals 1 to n. So that's the formula for standard deviation. So what we're doing is we're taking the deviations of each observation around the mean, squaring them, adding them up, and then we're dividing, and it's sort of like an average. We're taking the average, except we're using 1 over n minus 1 rather than 1 over n. And then we take the square root of all that. Why do we use 1 over n minus 1 rather than n? The full answer is in the lab manual. It is, I put a section at the end where I go through the explanation. For now, I will simply say that if we use 1 over n, that would give us a biased answer. But actually, I'm going to leave it. If you want to know the answer, we will get to the answer later on. But there is a good answer for that. One other thing, you remember last time when we chose the formula for the average or for the mean, we minimized this. So when we're using y bar, that means that for this particular sample, this is the smallest possible standard deviation that you can get. So the formula for the mean gives us the minimum size standard deviation. Another measure of the spread is the mean squared error. And that's pretty similar to the standard deviation. So we have the summation of the error terms, and then we just take the mean of that. The mean squared error, and we'll use this a bit, but this will appear sometimes, but it's not one of our main concepts that we use. Instead, what we use more typically is the variance, and it's almost the same thing exactly here. It's 1 over n minus 1 times the sum of the deviations. And you'll notice that this is the term that's inside that square root sign up here. So the variance equals the square of the standard deviation. So these are our measures of spread. This will get us pretty much everywhere we need to go. We've got 4 measures of spread, of which the variance is the one that we'll tend to return to most of all throughout the course. And you'll notice that we keep using these deviations here. Those deviations or error terms, they end up being really important in statistics. Okay, so let's move on, and now I'm going to talk about the concept of the sample versus population. So easiest to think of an example. Suppose that I want you to research and figure out what is the average income of Canadian truck drivers. The income of Canadian truck drivers. Well, you can conceive of the population. Okay, so you can conceive of the population, and that consists of all the truck drivers in Canada, however many there are. The population consists of all of them. But you can't talk to all of them, and you can't get information on all of them. That's too expensive, and there's no real need to. So instead, what if I got you to calculate the incomes of just 500 Canadian truck drivers? So this would be a sample. And most times in statistics, we don't have access to the whole population of something, so we have a sample. And what we do is we calculate information about the sample and then use that information about the sample to tell us something about the population. So if we have a good sample, then the statistics about the sample will tell us something about the underlying population. So the principle here is use sample values to estimate population parameters. And that is one of the essential tasks in statistics. Now I'm going to move on to a very important concept, so related to the mean, the expected value. The expected value, it's a different, a slightly different statistical concept, but when we apply it, we end up with the mean most times. So what is the expected value? It is the mean weighted by probabilities. Weighted by probabilities. So it's best to explain this with an example. Let's say we want to estimate the return on an investment. All right, so you are working at an investment company. You've assembled a portfolio of securities, and based on past data, your expectation is there's a 70% probability that the return on this investment will be 1%. There is a 10% probability that the return on the investment will be minus 10%. And there is a 20% probability that the return on the investment will be 5%. So, what is the expected value of the return on this investment? So first thing, the probabilities have to add up to 100%. All right. So, and that just means we have looked at all the possible outcomes. We've examined all the contingencies. So the expected return will be these individual returns weighted by their associated probability. So it's going to be, now 70%, we rate that as 0.7. So it's 0.7 times 1 plus 10% is 0.1 times minus 10 plus, and 20% or 0.2 times 5. So we've taken the returns and we've weighted each of them by their associated probability, and that equals 0.7%. That's what it works out to be. So the expected return on this investment then is 0.7%. Now what we want to do is generalize that concept, generalize the concept of expected value. So our notation is we're going to refer to the expected value of y equals the sum from I equals 1 to n, our sample size, the probability that y equals yi times that value, yi. So again, the probabilities all have to add up to 1, and this just refers to the individual observation that we observe. Now, if all the probabilities are the same, then it turns out the expected value and the mean are the same thing. And it would be possible to show that mathematically, but I'll just write it out. If all probabilities are the same, if every value is equally likely, then the expected value equals y bar, the sample average. Now, that's the expected value of y. We can also compute something related to it. We can also compute the expected value of y squared. It may not be obvious why we would want to, but we will have reason to do that later on. And if we want the expected value of y squared, well, we just use the same formula. I equals 1 to n, the probability that y equals yi times yi squared. So we square the variable in the formula, but not the probability. The probability stays the same, but we square, in this case, yi. Now, this refers to our sample of data. I'm using y and y bar to refer to the sample of data. For the population, the expected value of y equals mu. Okay. In other words, that's standard notation. And it just denotes the population expected value. It's not always the case that the expected value equals the mean, but when the difference matters, we'll try to remember to use the term expected value rather than the mean. Now, the variance, so I've already given you the formula for a sample variance. Now let me tell you where it comes from, the formal definition. So the population variance, instead of using s squared, we will use sigma squared. So that is the population variance. Just like mu here is the Greek letter for m, so it's kind of like the population mean. And to denote that we're talking about the theoretical mean of the population rather than a sample mean, we use the Greek letter mu. And here, sigma squared is s squared in Greek. So again, we're denoting that it's kind of a theoretical concept. It's the variance of the whole population. That is the expected value of y minus mu squared. So it's the expected value of the deviations of the data points around the population mean. And so if we apply the expected value formula, then that's going to be I equals 1 to n yi minus mu squared times the probability of yi. And I'm going to expand this out. So to do that, rather than zoom out, make it harder to see, I will just switch over to a different page. So sorry about this. All right. So we have sigma squared equals that expression here, and so that equals I equals 1 to n. Now here I'm just going to factor that out, or multiply two bracketed terms together, so I get y squared minus 2 mu y plus mu squared. All right, now mu is a constant. Mu is a constant, and with these summations, if you have a summation applied to a group of terms added up, then you can apply the summation individually to them. So it's distributive, we say. It distributes. So sigma squared equals, take the first one here, so it's the sum of I equals 1 to n of yi squared times probability of yi minus the sum from I equals 1 to n, that's I equals 1 to n of 2 mu y times probability y plus the sum from I equals 1 to n mu times probability yi. And I'm going to stop writing the I equals 1 to n, because I think you know that it's always there. So I'll just rewrite this out here. A sum of y squared times probability of yi minus, now I mentioned before, if you have a constant inside a summation, you can take it outside of the summation. So this is minus 2 mu sum of y times the probability of yi. So I just took the summation outside, and then that leaves this term inside the summation. And then over here, oh, I forgot, that's a mu squared. That's mu squared, it's constant, so we bring it outside the summation. Sum p, sum of the probabilities. Okay. Going down here, we have the sum of y squared times probability, as before. Now, we have minus 2 mu. What is this one here? Where's my blue pen? The sum of y times the probability of y. Ooh, that's the expected value. So that's just the mean. So that's mu. So we'll have minus 2 mu times mu. So that's minus 2 mu squared. And then we've got plus mu squared. And what's the sum of the probabilities? Well, that equals 1. Sorry, that's a bit faded there. That equals 1. So we have minus 2 mu squared plus mu squared. So this is the sum of yi squared times probability minus, well, minus 2 plus 1, so that's minus mu squared. And this is the expected value of y squared, that term that I showed you last time. So this is the expected value of y squared minus, and what's this one? Well, that's the expected value of y, but it's all squared. All right, so the definition of the variance then is the difference between the expected value of y squared minus the square of the expected value. and that is sigma squared. And sometimes the book, instead of writing sigma squared, will write the variance of y. And sometimes in these lectures, instead of writing the variance of y, I might just write v of y to denote the variance. Now, what is the importance of all of this? At the moment, nothing terribly important hangs on this. It's worth knowing, though, because it is a formula that will be used in some calculations, and it shows up later on when we start talking about regression analysis and some of the formulas that are involved in regression analysis. In the meantime, the main thing is I expect you to be able to follow those kinds of steps, those kinds of derivations. Let me, I said something about the rules about summations. So let's just write A1 plus A2 plus A3. We could write that as the summation from I equals 1 to 3 of AI. Now, if I multiply each of these by 2 times A1 plus 2 times A2 plus 2 times A3, well, that is just the sum of 2 times AI. And so you know from your high school math that you can take out the common term here. So that's 2A1 plus A2 plus A3. And that's why you can bring the constant term out. So then we're back to 2 times the sum. So that's why you can take the constant term out like that. And then similarly, if you're puzzled about why we can have an expression like that and take the summation sign through it, well, you can just write out a simple example. So let's say we have A1 plus B1 plus A2 plus B2 plus A3 plus B3. Well, that's going to be the same as A1 plus A2 plus A3 plus B1 plus B2 plus B3. And because the order of the operation doesn't matter when it's just addition. So this is the sum of the A's plus the sum of the B's. All right, so that's kind of like what we did here. We have 3 terms here, but we have A plus B plus C, and we're adding those up. Since the order doesn't matter, we can just have the sum of the first terms, sum of the second, sum of the thirds. And then here we're multiplying each term by the probability, so you just have to remember to distribute that term in there. So these are all linear operations. And if it takes a bit of refresher, don't worry, we'll give you lots of practice. Our next concept is correlation. And here we have a formula, R equals the sum of I equals 1 to n. All right, so we have deviations around y, and now we're going to have deviations around x. So correlation always refers to the relationship between 2 variables. So we'll call them x and y. So we're interested in the relationship between 2 variables, x and y. And so we have I equals 1 to n. And this is where we have the squared terms. And we take the square root, and I equals 1 to n of the x deviations. And again, take the square root. And this formula, it's a bit messy looking, I suppose, but this formula measures the tendency of two variables to move together. So why would it? Well, if you think about what happens with r here, let's say x moves away from its mean. And at the same time as it moves away from its mean, every time x moves above its mean, y also moves above its mean. So then these two things get big together. Let's say we're interested in height and shoe size. Well, chances are, as people get taller, their shoe size gets bigger. So if x goes above the mean, y goes above the mean as well. So what's happening up top here is one gets bigger, the other one gets bigger at the same time, so these tend to get big together. And so it's clear enough why r will go up when the two variables move together. Or if x moves towards its mean, this gets small, then this gets small at the same time. Then again, if this goes below the mean, the same thing. It's moving away from the mean. This is moving away from the mean. In the other direction, the minus signs cancel out. So this term gets large in a situation when the two variables move together. What we're doing down on the bottom here is we're just rescaling it so these would be in the units of whatever we had up on top. So inches or meters or whatever. This just scales it so that it always ends up fitting within a bound between -1 and +1. So r is always between -1 and 1. This looks like the standard deviation. In fact, it is, except we don't have the 1 over n minus 1 term in front of each one. So this is like the standard deviation of x and the standard deviation of y, and then that the square or the product of the deviations up on top. So it's kind of like we're taking the product of those deviations and then dividing them by something like the standard deviation of each variable. If r is greater than 0, we have positive correlation. If r equals 0, then that means there's no correlation. And if r is less than 0, there's negative correlation. Negative correlation means if x gets large, y tends to go in the other direction. So then a positive deviation here would correspond to a negative deviation there. That's why the signs flip. Now, why is it bounded between -1 and +1? Well, let's imagine that x and y are perfectly correlated. So whatever x does, y does exactly the same. So y and x are always perfectly correlated. What would happen then? Suppose x and y are perfectly correlated. Well, if they're perfectly correlated, what that means is x equals y. So our formula then will be, we got the sum of I equals 1 to n of y minus y bar times, now normally I would write x minus x bar, but since x equals y, it's just going to be y minus y bar again. And that's divided by the sum of y minus y bar squared times the square root of the sum of, now instead of x minus x bar, I put y minus y bar squared again. All right, so up here I've got two identical terms, so I'm just going to I'll move this down a bit farther. So I'm going to have the sum of y minus y bar squared over, now here I have the square root of this times the square root of the same thing. So all I do is take what's in the square root sign and drop the square root sign. So I have sum of y minus y bar squared. And I've got the same thing on the top and the bottom. So they cancel out and it equals 1. All right, so that's why they are, if they're perfectly correlated, then r equals 1. What if they're perfectly anti-correlated? Whatever x does, y moves in the exact opposite direction. Well, in that case, it would just be x equals minus y. So if x equals minus y, everything else is the same, it's just we end up with a minus sign up top there. And so r goes to minus 1. Also, and here's a kind of a groovy tidbit of information for you, r squared measures the fraction of y that we say is explained by x. All right, so going to the example of these two being perfectly correlated, if y and x are perfectly correlated, then that means x explains y. Nothing happens in y that isn't simply explained by x. So what would an example be? If you, on that happy day when you take out a mortgage, you will find out from the bank what your interest rate is, and the interest rate that the bank gives you will be it'll be something like the prime rate plus, let's say, 1/4%. All right, so that's r plus 0.25. All right, r plus 0.25. So your interest rate that you pay, we'll call that I, and your interest rate is r plus 0.25. It turns out that if one variable is just another variable plus a constant, they're perfectly correlated. You probably know enough at this point you could prove that. Might be worth trying that out. But that means I and R are perfectly correlated. That means the prime rate explains the interest rate, in this case, the interest rate on your mortgage. Nothing is going to ever happen to this mortgage rate that isn't determined by the prime rate. If you know the prime rate, you know the mortgage rate is to add 0.25% to it. So, but what happens if they're not perfectly correlated? What if your mortgage rate is the prime rate plus an adjustment, 0.25%, plus some other thing, like they might make a risk premium, or there might be some other factor that varies over time? Well, that means the prime rate explains some of the movements in your mortgage rate, but not all of them. So in that case, if we calculate the correlation and it's something other than 1, if it's less than 1, the movement of the x variable explains some but not all of the movement of the y variable. Or in our example here, the movement of the prime rate explains some of the changes in the mortgage interest rate, but not all of them. The fraction that is explained by x is r squared. And we will come back to that because the r squared score matters quite a bit in regression analysis, and so we use it a lot. Okay, so Now, one thing to be careful though about r squared is if you have a bunch of factors that explain a variable you're interested in, you can't calculate the correlations between all of them and add them up. R squared doesn't work that way. You could end up with your explanatory variables explaining 170% of what goes on in the y variable, and that doesn't make sense. So we'll talk about how to calculate an r squared score in a multivariate setting when you've got more than one explanatory variable. Let's move on. Try to finish up the rest of our material here. We have XY plots are good for illustrating correlation. That should be an N, not an M, for illustrating correlation. So look at figures 1.5 to 1.7 in the textbook, and you'll see some examples, and we'll see more examples as you do the assignments. But these XY scatter plots, as they're called, they're good for illustrating what correlation really means graphically. Our notation, R refers to the sample correlation, and if we write core x, y, that's our notation for the population correlation. Now, there's a related concept called covariance. Covariance is like correlation, except we don't have that scaling step to bring it all down to a range of -1 to +1. So you recall that variance equals the expected value of y minus mu squared. The covariance is the expected value of y minus mu of y, so that's the population mean of y, times x minus mu of x. So just the expected value of the y deviations times the x deviations. And we've kind of seen something like that already. When we had the formula for correlation back here, that's kind of like the term on the top there. So correlation is kind of like covariance, but it's scaled down to be always between -1 and +1. But it's the same idea here. If sorry, I'm just straightening out my notes at the side there. If y gets large and x always gets large at the same time, these move together. So the covariance goes up. If y gets large and x always gets small, that moves in the other direction, then covariance will tend to be negative. And if they don't move together at all, then the covariance will tend to be 0. So it does turn out that the correlation can be derived as the covariance. So I'll call this covariance of x and y. Covariance of x and y divided by the square root of the variance of x and the square root of the variance of y. And the square root of the variance is the standard deviation. It's also going to be the case that, although we won't go through this, the covariance of x and y is equal to the expected value of x times y minus the expected value of x times the expected value of y. And if you're wondering why that could ever possibly be true, well, if we go back to the perfectly correlated case, so x equals y, then that is the covariance of x with itself is the variance of x, and that equals the expected value of x squared minus the expected value of x times the expected value of x. That's the formula that we had before. So this holds true, and it's one of the little formulas we just doesn't mean a whole lot. You can get through life without it, but it's handy to have on the shelf somewhere, because the day will come when it will be useful to know that you can decompose a covariance term into these two these expected value terms. All right, so that's a quick tour of a lot of statistical concepts that you have learned already, but will need to relearn. And there are a lot of lab exercises this week, more than usual this week, because I want to give you some practice and refresh your memory of all these things. So good luck with the lab exercises. Get busy with the R programming, and I will see you next week.